So let's see. So I'm glad that those of you are here. Looks like you have some access to power and internet. For those of you who are watching this in the future so appropriately on YouTube, I hope you get the power and your internet so it's back on soon. I guess if you're watching it, it's already back on, or you're watching on your phone in a coffee shop or something like that. So we were told by the university lectures would go on. So here's the lecture. But I hope everyone is safe. Sounds like the windstorm should mostly be over at so at this point. So today we're going to talk about kind of a continuation of the use of the use of Bayes rules within data analysis. And so we'll talk about a slightly more advanced ideas. These are called Bayesian inference, but we'll start by kind of going through this this kind of an extension of that example we went through at the end, where we took this model and we said we have this data and we have this noise model in the data, and it came down to just an average, and this cool thing was the best choice to model. So we'll go through that a little bit more, and we'll make it a little bit more complicated and how to think about that and how to extend this idea. First, I just want to look at the schedule. So you should now be seeing the web page, and so this is kind of the last part of the basic chapter 1 probability, but maybe some slightly new stuff on how to use Bayes' rule. Then we'll be starting next week on some other stuff based on probability on convergence, on when you have lots and lots of data, how to get a better and better estimate of that data, and kind of the basic rules which apply here. You may have seen some stuff around the central limit theorem before. We'll talk about that, but then we'll say, okay, that's kind of a vague, kind of nebulous sort of object. We'll talk about how to actually use that in kind of get some more, when you actually have counts on the data, how to fit that together. But the other thing coming up on Monday is going to be quiz number 1. It's going to be on Canvas, just like quiz 0. We will open up the quiz like last time with 15 minutes left in class at 2:30. And then I will, this time I've kind of learned from that experience, we'll leave it open until 11:59. Okay, so you have all that time to do it. So it should be more flexible. You still only get half an hour to do the actual quiz. But it'll be like before. My aim is for it to take roughly as long as quiz 0. The average for quiz 0 is about 9 minutes. I think we'll aim for 10 to 15 minutes on average to take you, but you'll have a half an hour after you start. So this quiz will be on all the material up through today's lecture, and it should basically be stuff that if you've been following along the lectures, that you should be able to just write down the answer. Okay, so it should be kind of the core basic stuff to make sure you're really understanding, kind of following along what's going on in the lectures. So I'm going to have these be, so they are going to be so pretty much open book. You can use the book linked off of the web page. You can use the notes link off the web page as well. If you don't remember, if you click on these things right here, you actually get the notes that I am writing on during class. So you can click and use those as well. Okay, so if you haven't been following along and you have to look it up and learn it as you go, you might not have enough time. But if you've been following along, I assume you should be fine. But it's good to review the material before the quiz. So great. Any questions about the quiz or the place we are in this semester so far? So great. So all of office hours immediately after class, another good time to ask me. Otherwise, there'll be office hours for me tomorrow and Hassan's on Monday before class as well.
I actually have one quick question. Are there practice problems in the chapters that we can practice for the quiz?
Yeah, so the at the end of the chapter there are some practice problems. These are closer to most of them closer to the homework problems level of challenge. There's one just to kind of get a sense of what the quiz is like. I do have a practice quiz down here. This should be maybe a little bit more material than what you have in a single quiz. This was from last semester when we had only 4 quizzes instead of 6 or 7 this semester. But it should give you a sense of what it's like. It'll also be a little bit different because it's going to be on Canvas instead, but that's kind of give you a model of how challenging these things should be. Okay, but I don't, the ones in the back of the chapter are in the textbook, are on the right material, but they're typically a little bit things that you would take time to dwell over a bit more, like on the homework.
Okay.
So, but I don't have a full practice quiz for this quiz.
Okay, thanks.
Yeah. So great. So let's get on with the lecture. So we're going to be talking about Bayesian inference. Okay, and so if you remember from last time, we're basically talking about Bayes' rule. Okay, and so this was, and I'll write down a simplified version of this for random variables m and d. You want to compute essentially the probability of m given d, so the probability of a model given the data, and then we talked about finding the maximum probability model, right? Instead of equal, we're going to, well, I'll write this and then replace the equal. So we used to have probability of data given the model times the probability of the model, which is a prior on the model, divided by the probability of the data. Okay, so we're going to simplify and change a couple things about how we talk about this today. So first, we're going to replace this equal sign with this. I didn't draw that very well. With this symbol. Okay, and so this is saying that it's so proportional to. So it's proportional to the right-hand side. And that allows us to remove this part on the bottom. Okay. Okay, so what this is saying is that now we have a simplified version where the right-hand side is just the left-hand side, the probability of the model given the data is just proportional to the probability of the data given the model times the probability of the model. Okay, so proportional to f of x proportional to g of x, it means that f of x equals c times g of x, where this is a fixed but possibly unknown, so constant. Okay, so this was in the cracked windshield example we did first. This was the probability that the windshield was cracked overall, and we looked and we didn't need this to find the most likely factor that was doing this. Okay, so we didn't need this constant factor. Okay, and so when you're often dealing with Bayes' rule, you often ignore this thing, and use this proportional to. And this is useful when you just want to find, say, the maximum likelihood model. Then you don't care if the probability is multiplied by by 8 or by 1/10 or something like that, that's not going to affect which is the most because that's multiplied by everything. Okay. Then what we did in the longer example that we focused on in last lecture, which was a week ago, is that we also got rid of this term. Okay, so this term was known as the prior. Okay, and so we talked about this we had ignored this term as well. We said that was also constant. Okay, and then you get the probability that the models given the data was proportional to the probability of the data. So given the model. So we're going to work through today what happens if this is not constant, and so try and factor this in as well. But so in that case, if it's not constant, then I have to include this term here. Okay, so this will be our simplified version of the Bayes rule. So okay, so the other issue with it though is that we want to talk about models, and we did this in an example yesterday, and we were kind of cheating a little bit, but the probability of a model, the space of models was actually continuous in this example where we find a single point estimator to kind of end up being the mean of a distribution. And so we can't actually write down the probability. We can only write down a probability density function instead, right? So we're going to change these now to be probability density functions, okay? And so I'm going to write, and they typically have functions, so we're going to use lowercase letters or Greek symbols to represent them. But these are probability density functions now. So we're going to model given the data is going to be proportional to f of d given m times pi, and this is another function of the model. Okay, so these are PDFs. So needed for continuous. So for continuous random variables. So okay, so when we do this, then we'd already talked about that this one is called the prior. Okay, so this is usually our prior knowledge about the situation. And up until now, we've kept this, so we didn't have any prior knowledge. So we said all the models were just equally likely, and we'd factor this out. But we'll go through an example that changes this. A couple of examples. And then this one is called the likelihood. Okay, this is the likelihood of the data. So given the model. And when we found the model which maximized this term f, okay, and when we ignored the prior, this was called the maximum likelihood estimate. Okay, so that was maximizing this function with respect to the value of the model. Okay, and then when you combine these together, you take the product of these. The right-hand side is called the sorry, the left-hand side is going to be called the a-Posterior. Okay, and we said at the beginning that finding the model which maximized the choice of model given the data was the map estimate, the maximum a-Posterior estimate. And so that's when you incorporate the likelihood and a prior on the model, then it becomes a map estimate. Okay, so when I find the maximum model for the just without the prior, that's a maximum likelihood estimate. When I have the maximum model given the data and the prior on the model, that's a map estimate. Okay, so we'll go through a map estimate example today. So, when you have continuous space of models and data, in this case, the right way to do this is with probability density estimates, because the values at a particular point don't make any sense as a probability. Okay. Okay, so all I've done is change the notation. I haven't really changed kind of the mathematics of kind of understanding or calculating anything now. I've just kind of fixed some stuff that we cheated on in the notation last time to make it a little bit more intuitive on a first pass. Okay, so I haven't really done anything. Okay, and again, so last lecture, we said, okay, so if the probability, or if the PDF of the model is constant for all choice of the model is constant, or it could be over a continuous set of things, and then you can't quite say it's constant, but you can still kind of ignore it, then this is what's called a flat prior. And in that case, then you just need to worry about the likelihood, okay? But so we talked about last lecture about a flat prior. Now let's say we actually have a prior, okay? So that's what we're gonna go through and just do some simple example first on that. Okay, so let's talk about an example now where we're gonna do this, and we're gonna talk about, we have some, what we wanna do is to estimate, a model is going to be H, and this is going to be the height of, so let's say university students. Okay, so we want to estimate what is the height of university students. Okay, and like before, we're going to have some data. We'll call this D, x1, x2, up to xn, and these will be a subset of these real values. Okay, and we'll assume some sort of, probably some, like before, we can assume some Gaussian noise on this. But before we talk about that, we're also going to have a prior. Okay, we're going to say, well, I've got some prior knowledge about what I expect the height of an average university student. Okay, so I'm going to have a prior on H. Okay, what I expect the height to be. You know, this is my prior knowledge, but let's say I say that this is the mean is going to be 66 inches. Okay, and then this standard deviation, and let's say I know that this varies. Not everyone is exactly 66 inches, which is going to be like being 5'6". So the standard deviation is going to be 6 inches as well. Okay, so this is my prior knowledge about that. The average person is about 66 inches, and this standard deviation is about 6 inches. So if I don't get any data, this would be my guess of the average student at the university. Okay, and so we actually want to make this a probability distribution. So we'll use that the prior, right? So we'll say that the prior on H is going to be a normal distribution with a mean of 66 and a standard deviation of 6. Guess it's been a pretty kind of strange year. And we'll put this, so this is a normal distribution. And if you remember what this is, I'll write this out, plugging in the mean and the standard deviation. I'm gonna get 1 over square root of pi times 72. There's a 2 in there, and there's the standard deviation squared, which is a 36. That's going under there also. Then it's x, and that's just a normalizing constant, minus, so the mu of H, the true mean value of the height, which is what I want to estimate. I want to say that my expectation is this is 66 inches squared, and I need to divide this all by 2 times 6 squared. Right, this is all inside the exponential. Okay, so this is the a normal distribution with a mean of 66 inches and a standard deviation of 6 inches here. Okay, and so this is my prior. Now I've put a PDF in place of this prior in this estimate, and now I can factor this into the into the posterior. Okay. Okay, so I'm going to go and do that, but I first want to say before you actually work through the mathematics, there's something else useful you can do with the prior. And so let's say, as an example, so let's say that my maximum likelihood estimate without the prior, right? So this is without using the prior, and I did this based on just the mean of my data of X, right? This came out to 5.5. Okay, so let's say I did this independently. I knew how to create my estimate without looking at the prior. So let's say I went and did this. And now, and I get an answer, which is 5.5. Now I wanted to combine it together with my prior knowledge. And remember, the prior knowledge said, okay, that's 66 inches with the standard deviation of 6 inches here. Okay, and I want to compare that to 5.5. Well, the first thing I should see is this is a pretty big difference. I'm pretty far from my prior. So what's probably going on here before I do any sort of calculations? So the maximum MLE question is, what does MLE stand for? That's the maximum likelihood estimate. Maximum likelihood estimate. All right. If you remember what the maximum likelihood, remember the likelihood is this term here. So that was the estimate just by looking at the data, right? I found the model which maximized this, and we did this in the last lecture where we we assumed there was some Gaussian noise on the data, and we found it doesn't matter what the standard deviation was, as long as it was Gaussian noise, then the model which maximized this quantity was going to be the average of all the data points, which was this term right here. So this is the average of the data points. That's the maximum likelihood estimate if I assume Gaussian noise on the data I have. Okay, so with just looking at the data, I got an answer of 5.5, but my prior said it should be 66 inches. 5.5 and 66 are pretty far off. So what's probably going on here? Feel free to, good. I have an answer in the chat. So someone says feet instead of inches. Yes. What's probably going on here is that this is measured in feet, and this and the maximum likelihood estimate, my data was in feet, and my prior was in inches. And so if I multiplied my maximum likelihood estimate by 12 times 12, I'm going to get exactly what is this going to be? 66, right? Oh, perfect. Oh, okay. That actually makes a lot of sense. Did I do this? Yeah. So if I multiply it by if I convert from feet to inches, then I get back exactly what my prior was. Okay. So it can tell me this without doing any extra calculations doing this. I should kind of think about the units here, and if they're way off, then before I start just blindly doing calculations, I should look at the units. Great, good. So this is kind of the first thing you should do with the prior. Okay, don't just blindly go with the math, right? This is about, I guess, the kind of the foundational stuff, and it's not, I personally love the math, but it's not all about the math. It's also about using your common sense about how these fit together. Okay, Great. So so um, so so um, so okay. So let's go and see now how the math would work, how I would do this together and find the maximum a-posterior estimate for the model, where I took some data and some of the and some prior and combine these together. Right. So as it turns out, it's not going to be too hard. Okay. So now if I want to put these together, what I want to do here is write the remember the likelihood was, I could assume that each data point xi was from some sort of also from some normal distribution, where the true value was the true mean of the height, right? It was unbiased, but it has some noise, and the standard deviation was now 2 inches, right? And just to be clear, we're dealing with inches here. Okay, so I have the right units on stuff now at this point. Okay, so I'm drawn from some normal distribution. Okay, and this is my distribution for the model. That's a normal with a mean of the true value, and a standard deviation of 2 in inches in this case. Okay, and we're going to assume that these are that these are going to be independent. Okay, so everyone drawn from the population, every point I pick, every reading I get, I draw that independently from someone else. So I want to get the things at the University of Utah. So I look up, I pick a random ID, UID, and then I go and I find that person, and I actually measure that person, and maybe I get some noise in this, Gaussian noise in this process. Probably not Gaussian noise, but for simplicity, we'll talk about Gaussian noise here. Okay. Okay, but each of these was independent. I could pick the same person twice. Okay, so what that's saying, and because of independence, this means I can write down that the total probability of all these is the product. Okay, again, looks like a big pi sign, but it's a little bit different. Of all the data points I've collected of some Gaussian kind of model here, right? Or this is this normal distribution. I'll use g of x. Okay, and let's write this out. This is the product of x and d. Now I have 1 over square root 8 pi. And this is because the standard deviation is now 2 instead of, this goes into the 8. That's actually 2 times 2 squared. Okay, so and then I have negative 1/8. This is again from the standard deviation of the true. Yeah, and this was the model. Here's the height. Okay, and of the true mean minus x squared. Okay, that closes the exponential and closes the product. Okay, great. So this is my is the likelihood. Okay, this is the likelihood of the model given the data. Oh, what are you referring to when we say noise? Yeah. So this is a tricky question. When you're doing some when you're trying to formulate this as a mathematical expression, you in this model you often say that the data is not a true representation of the true height of every student. I'm getting some measurement, something which is an approximation of what the average height of a student is on campus. There's actually the process I described actually has other types of noise which is going into this. I'm picking one representative instead of kind of instead of measuring the you know, everyone on campus. And I also might actually, when I measure them with the tape measure, they might be squirming or something, or they have a different hairstyle or something like that, which is changing what the actual measurement I get is. So for simplicity, and because the math will work out easy, we're going to assume it's Gaussian noise. And this is just a standard thing to do. But you could replace this with other models, and that would change what this expression is. For a lot of the rest of the class, we'll kind of not discuss this as much, although this, and we'll kind of assume that's Gaussian noise because you end up getting convenient expressions, and we'll try and that's standardly what you do in machine learning data analysis. But I think it's a great question, and this kind of comes into some implicit assumptions about what's happening here. Okay, what does the pi symbol represent? Okay, so this symbol here, okay, looks kind of like an uppercase pi symbol. It's actually, if you write this in LaTeX, it's actually prod. Okay, it's like it's a product over a set. Okay, all the elements. Remember, I've got some set D, which is my data, which are going to be x1, x2, up to xn. Right? This is a set, and I take the product over all the terms in the set, just like you would a sum. Right? The sum looks like an uppercase sigma. It's actually, again, a /sum inside of LaTeX. They're slightly different. Okay, but that's what this uppercase pi symbol is representing. It's a product over a set. Okay, and we'll convert it into a sum with the log transformation in a second. Yeah, so you won't necessarily be expected to memorize exactly the formula for a Gaussian distribution, but you should know it's some coefficient times an exponent to a difference to the negative of a difference squared. And there's some normalizing thing that has to do with the standard deviation. That will play a role today. It will then mostly not play a role until we get to clustering, and then we'll look at it again. So the coefficients in front of everything aren't so important, but the main part of this, I think, is worth understanding, right? That the Gaussian looks like the e to the power to the negative power, the difference from your value squared. Okay, that's a pretty kind of fundamental thing you should know. It'd be good to know how to combine these data points together, right, into a product, and kind of this one derivation kind of will explain and justify a lot of the formulations we'll use later on in the class without explicitly going through this derivation. So I think it's worth knowing this. That's why I'm kind of spending most of 2 lectures on it. Where's the but for different distributions like the Laplace or the Cauchy distribution, those are different. You can look them up, but in this class, they're not so important. Those are things you should look up. The Gaussian is going to show up like every 3rd lecture. So by the end of the semester, you should definitely know what a Gaussian distribution looks like. Okay, so where does the 1/8 term come from? Yeah, so the 1/8 is 1 over 2 times the 2 is not squared. It's 2 times sigma squared. All right, so this guy is 2 times sigma squared. Yeah, so that's where the 8 comes from. Good. Okay, so great questions. This is important, so I'm glad we reviewed this a second. Okay, this is the likelihood of the distribution, and this is kind of a fairly standard thing. Gaussian noise on the data, likelihood of distribution, you take the product because they're independent. Okay, but now let's go back to this, and we want to get the posterior estimate instead. So we want to get the model of the height, or the probability, or the probability density of the height, which is our model, given the data. Okay, this is the posterior. And this combines the likelihood, right, which is f of d given h, Okay, it combined this, which we just discussed, times the prior, right? This prior was lowercase pi of h. Okay, this lowercase pi of h is here. We can replace this by f of d times h. Let's write this out now. This was our normal, again, normal distribution with a, this was a, remember, this was our normal distribution with a mean of 66 and a standard deviation of 6. So we can plug this in here. And this is now 1 over square root pi 72 times exponential, okay, minus mu of the height minus 66 squared divided by 72. Okay, so look, again, the same structure of the Gaussian or the normal distribution has come up again. Okay, and now we want to find the maximum likelihood model, in this case for the height, of this expression, where we combined together kind of this likelihood function, which shows up here, times the prior, which is the right term. Again, it's a product, okay? And so what's going to be simpler to do is to instead look at the log transformation. We'll use the natural log. Okay, we'll look at the log-posterior. Okay, this is a log of p of h, because if we just want to find the single most likely thing, then we can do this monotonic transformation by a log, because we know it's greater or equal than 0. Okay, and that the log allows us to turn a product of terms into a sum. Okay, so we have f of d given m, okay, plus the log of the prior. Sorry, this is, we're using h for the model, this example. Okay, great. Okay, so now I've turned this product of likelihood and the prior into a sum. This is similar to what we did before, and in fact, we can write this by now expanding the kind of pushing the logarithm into the definition of the likelihood, because remember, the likelihood has a product inside of it as well. So we can expand that also out into a sum. Okay, x in d, and this was minus 1/8. Right, so there was an exponential, but the natural log canceled the exponential. Okay, and minus 1 over 72 times, and I can do the same thing here of minus 66 squared. Okay, I dropped some terms that had to do with the drop some terms that had to do with the pi, so I'm going to add a c here. Okay, that had to do with the actual kind of constant lowercase pi, because those are the same everywhere. Those are both, and so I'm just factoring them out. Still, they're still proportional to, because I'm using this proportional to symbol. I don't care about constant factors, and there could be these additive terms as well. Oh, and so this also has an additive term, but again, for the maximum, this won't matter. Okay, should the sum still be an uppercase pi? Okay, so this Yeah, so let me just say again about the log transformation. If I have an expression which is the product over a set D, and let's just say this is f of x. Let's say this is g of x. Okay, and I do a natural log of this. This is equal to the sum over x of d of the natural log of g of x. Okay, so this is a cool thing about the log transformation. It turns a product, again, this is a product into a sum. Okay, so this is a really important kind of trick that happens here, and that's what's going on here. I've used that twice, in fact. Okay, I've got the high level, the product between the likelihood times the prior, and I've separated that in the first line. Okay, after I've done the log transformation, I've done the log of the sum of those two terms, each with the log transformation. Okay, and then this directly, I just the prior is then and has an exponential term, and I directly turn that, you know, just use the log of that. Okay, and it had a coefficient. That coefficient, kind of this coefficient down here went into here. Okay, that coefficient was also a product, and I kind of got pushed that to the side also. So that went into the end, into the end there, or actually went down to there. Okay, there's another C that happened possibly because of the probability of the data or that I didn't need to worry about. Okay, when I did the log transformation, that becomes a sum. Okay, so there's this other coefficient I also can factor out down into this, an additive term there also. Okay, then the second time I use this trick, this log sum product trick, is in the definition of the likelihood. Again, I expanded that out. That again had a product over the Gaussian noise, and I turned that into a sum of a bunch of things. So I've got a sum in the first term plus something else, plus all those coefficients, which didn't matter so much. Okay, so that's where all those pies went. All those products turned into sums. Okay, good. So we're almost done at this point. I'm going to do one more step, so this is a little bit more readable. Okay, I'm going to say that this is proportional to minus a single sum, or a sum over x and d. Remember, if this is off the bottom of your screen because you're on full screen, if you go out of full screen, you'll be able to see everything, times 9 times mu of height minus 66 squared plus a constant. Okay, so now what's going on is that I am so proportional to, so I've multiplied everything by 9. I can also do that in the case of something is proportional to something else. But what's a little more clear now is how to think about this prior in this case. So this is, I've got two terms now. Okay, I've got this term. So I've got this term which is coming from the likelihood, and then I also have a term here which is coming from the prior, and I'm added them together before, and I want to find the maximum value of this with a negative in front. Don't forget that that there's some negative term in front. So I still want to find the maximum. If I get rid of the negative sign, then I want to find the minimum. And this is, again, a proportional to sign. Okay, so now this looks almost like we had before without the prior. Because I have Gaussian noise on both of them, they both ended up becoming the sum, or a bunch of terms where I have the difference from the true value I want to find squared in each of those terms. Okay, this minus sign shows up here also. Okay, yeah, so they both look basically the same. Okay, the only difference now is that I've got a 9 in front of some of them, the ones from the likelihood, and not in front of the prior. And this stems from the choice of the standard deviation of the noise models I chose, right? So I chose the noise model for my prior to be a standard deviation of 6, and in my likelihood, a standard deviation of 2. So that's where it factors in. And what that means is that each data point I get now, each one of the x data points is worth 9 times as much as the prior. Okay, now that was a modeling choice, and that's where it went in here. If I changed those standard deviations of my noise, then I would change this what this factor is. Okay, so if instead, so probably what happened is that, you know, I said, well, the population itself has a standard deviation of 6, and I used that in my prior, but that was, again, probably the wrong thing to do. That's not my estimation of the mean, the expected value of the height of students. That's the population kind of standard deviation. Okay, and so as we'll see in the next couple of lectures, is that as you get more and more data, that standard deviation should actually go down. If I have a lot of data from the population of the US, and that's what's driving my prior, then I should have a much tighter estimate around my mean, right? So maybe instead, so if instead I set my standard deviation to 0.1, then that prior is going to be worth a lot more. Okay, so let's go. I've got a lot of good stuff on this slide, but I'm going to go to the next slide and kind of work this out. Okay, so we're going to look at how the weight of the prior plays, kind of a little bit where that comes from, and how to think about that. Okay, so of prior. Okay, so what happened there? I'm not sure why. Oh, okay. So we're gonna. Someone's asking the question we're just gonna talk about right now. Great. So in the first thing we had that our data D, we had that X was from a normal distribution with the true height, and the standard deviation here was 2, and we had that a prior, which was P of H, was equal to a normal distribution with 66, which is an input value, with the standard deviation of 6 instead. Okay. Now it turns out we're with the Gaussian and with standard deviation, with variance, we're dealing with squared quantities, and what we ended up squaring this term inside of the normal distribution. Okay, remember, it's normal distribution was some squared quantity inside the exponential divided by 2 times the standard deviation squared. So if you square these to get the variance, okay, so the variance here is 4, and the variance here is going to be 36. So the variance is a lot higher, and the ratio between 4 over 36 is equal to 1/9. And that's kind of where it comes from. In this expression, I got a 9 here specifically at the bottom because I multiplied everything through by 72. just so the prior had a weight of 1. So I just multiplied through by 72 to get that 9. But that's just so you can see this a little bit more clearly. It's that ratio which really matters. Okay. So that's what's going on here. Now let's say instead that this value here, this was wrong. Okay, I want to say instead that was a population standard deviation, not my trustworthiness of it. My trustworthiness of, say, the average height of a person might be much higher. So I'm going to change this to 0.01. Okay, and then if I go through that, or let's say 0.1, then this becomes 0.01, one of the variance, and then the ratio of 4 over 0.01 is going to be 400. So what this is saying is if I do this now, the prior is worth 400 data points. Okay. So if I had 400 pieces of data, then it'd be worth one of the priors, right? I'm going to get an expression where after I normalize, it'd be x minus mu of h squared plus 400 of 66, which is my prior, minus x squared. Okay, now the prior is worth 400 of these data points. Now I'm, okay. And so when I solve for this, it's going to be worth, as if I had 400 data points, I can just throw these into my average. Okay. Otherwise, if I need to have if it's worth 1/9 of a data point, I pretend I have 9 examples of every data point, and then I throw it into my average and I solve it the same way. It's like another data point in this case, because they're all Gaussian distributions. If they're not Gaussians, then I have to do more work to solve for this. I can again maybe take the derivative and solve for the minimum or maximum value, depending on if I have a minus sign. Okay, but so by changing my confidence, the kind of the tightness of a prior distribution, it's worth more or it's worth less in terms of the number of data points. So this is often a pretty intuitive way of thinking about it, but this only worked because they both had Gaussian norms. If not, then becomes just a mathematical expression. There are other ways to derive it and mathematically, but I think this is a nice way of thinking about it. So, okay, so if this happened and then I took 10 measurements and the prior is worth 400 times, then my data points aren't going to affect my prior very much. Because it's worth 400 of these data points, I've added 10 to the average, that's not going to change it very much. Vice versa, if it was only worth 1/9, then if I had 10 data points, those 10 data points are going to really pretty much give me most of the answer that I have. Okay, can you explain the ratio of the variances between the data and the prior? So what is this talking about? Okay, so where this is coming from, let me go back to this expression. Look at the very bottom of the screen now. And I've got this expression, and I want to find the maximum a-Posterior prior. That's the maximum model for height that factors in the likelihood and the prior distribution. And I want to find the maximum, the log of that doesn't change what the maximum is. And I end up deriving this expression at the bottom. And what happens is it's the sum of this model. I want to find the mu of h, the mean of the height that I want to solve for the best estimate of. That shows up that's showing up both here and here. That's the same expression. It's a sum of things minus x, or 66. So 66 works kind of like a data point here in the prior, except that there's a weight in front of the data points of 9. This 9 came from because I chose 8 here, which came from this standard deviation, versus the standard deviation on the prior was 6, and that led to a 72 down here inside the exponent. Okay, And the ratio of 8 to 72 is 9. And so that led to where that factor is. And so I'm kind of helping you think about how to examine how powerful is the prior? How much is that influencing the solution versus the data? Okay, and there are trade-offs in doing this. Some of this is modeling that you yourself put into the problem, and then this is the mathematics to understand what's going on behind that modeling and how that gets influenced. Okay, so I want to do one more thought experiment, right? So the black part was the original. The red is if I decreased the standard deviation of the prior, means I have more confidence in my prior estimate of 66. So it's weighted 4 times as much. So if I did this with, if I assume that you students in the class were kind of a random sample, then they're only they're kind of roughly about 100 people in the class, a little bit less than 100, but 100 is less than 400, right? So that the students in the class, I would trust those less than the prior, right? This sum, right? I've got a sum here, right? This is, there's some number of data points I have, right? And if this is 100, then I trust the prior more. Okay, but if I get more data, but if I said that the size of the class becomes 10,000, right? I have a much bigger class. I look at all the freshmen at the university, and let's say that's 10,000. Then I am ultimately going to trust the data more than the prior. So if you get more and more data and you fix your knowledge about the prior, eventually the data will say, I'm just going to trust the data. I'm not going to ignore my prior thought about this. Maybe if students at the university, maybe students in Utah are taller than the average person in the population. So at some point, I'm going to start to trust that data even more. And that's kind of what's going on here. As if your prior is worth more, then if you're pretty confident about that, then you need a lot of data to kind of overrule that. But as you get more and more and more and more data, eventually you start to trust the data more than the prior. Okay, a couple of questions. Is the prior worth 1/9 of the data point, or is the prior worth 1/9 of the weight of all the data points? Okay, it's 1/9 of one data point here. If I look back in this expression, this is the sum is just on this one data point here. This is the sum is here, and then I have essentially one data point in the light blue outside that sum. Okay. Yeah, so that's it's worth keeping in mind here. And then when we're talking about a prior, is that referring to a previous data set that we were using to compare the current set? It could be a previous data set. It could just be from someplace else. There are lots of ways you can think of a prior. One place where this comes up a lot right now is in polling for like the presidential election. And the prior used by, say, the 538 website kind of comes from lots of different places. There's some knowledge about which pollsters are worth more, are more trustworthy, and then those get some weight which is higher into some average. And some pollsters have some bias to them, and that gets factored in. So I take theirs and I shift it by some amount. But that estimate of how trustworthy the pollsters, that came from some prior sampling of their data. So it probably eventually comes from some previous sample, but it might be filtered through because they were polling a different set of people or for a different election than this one. So maybe I downweighted it in some way. And this is kind of black magic. This is maybe not black magic, but it's kind of modeling that goes on here. And that's the choice of how you set up the problem. There's not some formula from a textbook that you can just, okay, let me copy down this formula. Here's how to do it. You kind of need to kind of figure out how you think these things fit together. And part of that's from data, and part of that is going to be from your own judgment. And as much as the mathematical side of me would like to kind of remove that part of the equation, that's really not the right thing to do. You need to kind of try and put some common sense into here. Yeah. So it could be from another part of data, but it might be filtered through some other assumptions you have. And so the prior is supposed to encode these sort of assumptions. So, okay, and depending on how you adjust it, it gets more or less weight in the final average that you actually get. Okay. Okay, I want to quickly say something about the computation of these quantities. I think this is pretty intuitive, but you often want to do something called a weighted average, and that's where you're going to get a set. And hopefully this just makes more clear what's going on. But you're going to get a set of points, say x1, x2, up to xn, and these come with their own weights: w1, w2, wn. Okay, and the case that we looked at before, you could think of, well, let's pretend that maybe there was an n plus 1, which was 66, and this is the weight, n plus 1, and this was 400, and each of these was equal to 1, right? This was a case where we weighted the prior times 400 of the data points. Then this prior, this value 66, got this, and all the data points were weighted the same as each other. Okay, but this could be a more general sort of thing, right? So we're going to focus on this case. Okay, so let's say they could be any sort of weights. And let's say we have n for ease of computation. Then the weighted average of xw is then, you've probably seen something like this before, but this is just wi xi times divided by the sum of the weights of all the averages. Okay, so the sum of weights kind of with the prior example was n plus 400. So maybe we had n 100 data points and the prior is worth 400. So I'm dividing by 500, but that weight shows up in the numerator and the denominator. Okay, if we have a uniform average, so kind of the common example is a special case, is when each of the weight wi is equal to 1 over n, right? And then we get that we have 1 over, so it could be each of them has a weight of 1, or I get the 1 over n times kind of the sum over I of xi divided by the sum equals 1 to n of 1 over n. Well, this is equal to 1 over n sum of xi divided by 1, right? The denominator in this case is 1, and okay, so I can just ignore it, and the 1 over n factors in front, and that's just the average, right? So this is a generalization of the weighted average, and if I have, remember I had these values 8 and 72, or 1 over 8 and 1 over 72, and I multiplied through by 72. Well, I just changed the weight by a constant factor everywhere, then that cancels out here, right? So if I multiplied by 72 in the numerator and the denominator, for instance, let's say I put a 72 on the numerator and in the denominator, well, that cancels out. So that doesn't change the weighted average. Okay, so yeah, so I can also have, so this is also why that did not change my answer to the most likely, the maximum a-posterior estimate by multiplying by a constant factor. Okay, so if I get a prior with one weight and the data with other weights, then I can combine them together with the weighted average. That's kind of technically the right way to do it, to think about it. Okay. So I want to say, okay, so this was kind of basically the kind of working through so far this very simple example where I have a bunch of real values and I want to estimate what they are under, if I assume Gaussian noise and some prior, the maximum a-posterior estimate. And it basically comes down to something, right? So if I have data plus Gaussian noise, I should say this is independent Gaussian noise, then this is going to come down to the maximum likelihood estimator, okay, is going to be the minimum, m, m, that's going to look like the sum, or xi in d of xi, so minus model squared. This sum of squared errors. Okay, so this sum of squared errors is going to show up. This is a sum of squared errors. This is going to show up throughout the rest of the semester and in much of machine learning and data mining. Okay, so this is a quite common formulation. This will often be our starting point here. If we add a prior, okay, then if this is a Gaussian prior, remember it's a PDF. So if we have a Gaussian prior, then it's going to become a weighted sum of squared errors. Okay, so it's basically, we're going to have another very simple solution. Okay, is one way of thinking about this, and we will, I think we won't actually see this in class, but one way this shows up elsewhere, at least if you get to data mining machine learning classes, is it eventually will take a sum of squared error solutions or a different type of formulation of what you would try and solve for the problem, and it's going to try and regularize its problem. It's going to try and bring you back towards a simpler solution or one that maybe fits some prior knowledge about it. And you get some extra term in this sum of squared errors. So it's going to be, again, you're going to get some formulation, the data points, xi minus some model squared plus some regularization term on the model. And this basically looks like what this prior is doing. So this prior ends up factoring into this regularization term. And this will show up in these models also. But there'll be a sum of squared errors plus this. In the case of, if it's a Gaussian noise, there'll be a nice, simple closed form solution in a lot of cases. But otherwise, I'm going to have some other term that I'll deal with in other ways. And we'll use, say, gradient descent or some other stuff we'll see in this later in the semester to deal with other sorts of terms here. So great. So this is one of the takeaways you should get from this. By modeling it as Gaussian noise, doing a log transform of the likelihood, you get this sum of squared errors formulation. This will just show up everywhere. Okay, but before we get with the last 10 minutes of the lecture, I want to say a little bit more about this posterior. Okay. Okay, so this posterior distribution kind of is this can be a really powerful thing. And this idea of Bayesian inference, which I mentioned in the beginning, goes much beyond what I just talked about. I just talked about the maximum a-Posterior estimate, which is the simplest form of this. We have an entire graduate level class that's taught on maybe most years or every other year that just talks about these Bayesian approaches to data analysis. And there are kind of three other things that, like, so the starting point is the is say the max of model of this posterior of the model given the data, right? So this is the map estimate. Okay, and this is what we talked about doing, but there are kind of like at least three other main things that you can do with this. You can kind of compare effectively the posteriors, and this is true of likelihoods as well of models. So I can write down an expression for, let's say I have two models, 1 and model 2. I can write down, I can't say what is the probability of the model. I typically can't write that down, but it is fair to do something like the posterior of model 1 given the data divided by the posterior of model 2 that's given the data. And I could say that model 1, so let's say, for example, that this is 1.3. Okay, then I say model 1 is 1.3 times as likely to be the right model than model 2. Or let's say this is 100, right? Model 1 is 100 times as likely to be the model as model 2, right? So if I was trying to debate between two different models, if the ratio is 1.3, I say, okay, those are pretty similar. Model 1 is better, but model 2 is still pretty good. Seems I don't have that much trust in it. But if the ratio is 100, then I can say, okay, model 1 is definitely much better than model 2. That's a pretty big difference. Okay, and so I can measure these ratios. Although I can't get actual probabilities, these ratios are things I can actually measure. And this allows me to kind of understand how big of a difference in kind of I'm fitting the data according to my assumptions does one model do than the other model. Okay, that's one thing you can do. I can also marginalize over models. Okay, so the ultimate goal is often not going to be to find the best model. That's kind of a pretty good proxy goal. It lets me do a lot of things, but it's actually to make predictions on new data. So let's say I've got a new data point, x prime, and I'd like to figure out, okay, what is the probably outcome of this data point? So far, all of our models have been simple, has been a single point estimate. Okay, but it could be that I'm predicting of a value, a return on investment on a stock, or on taking on a customer, or on buying a product, or something like that. And so what I actually want to do is take a model and apply it to here, and I get some value, right? And I want to say, how good is this value? Well, if I just have one model, I plug it into that one model, I get one value, but I can marginalize over models. So if I have a kind of a distribution on models, I can actually kind of use that to weight the models. Okay, and this becomes just a weighted average. So let's say I've got models 1, model 2, and model 3. Then I can say something like my estimate v hat is going to be my posterior of model 1 given the data times use of model 1 on this data point, plus the posterior of model 2 given the data, times applying model 2 on this data point, plus the posterior This is model 3, right? So I can take the 3 models, I can basically get a weighted average. Then I need to sum over as with the weighted average, I need to sum over the posteriors, kind of run out of space here, right? But I need to sum over the posteriors of the models to make sure that this is actually, I'm not scaling this incorrectly. Okay, so again, because I'm dividing by the posteriors on the top and the bottom, it doesn't matter what the factor is. I'm basically taking the ratio of them in this case here. And now I can get an estimate that combines them based on how much I trust the models. Maybe I trust model 1 and 2, our ratio of 1.3, so I kind of want to use both of those. And model 3, maybe it's unlikely, but it gives a very different value. Maybe it's worth 1/100th, but maybe the value is very different. So I want to actually kind of take that into account. Okay, and this allows me to kind of take all my knowledge about the space of models into account into an estimate. Now, if the space of models gets very big or is continuous, this becomes much harder, more expensive to do, but it gives you a more robust estimate of what's going on here. Okay, and then and then the other thing you can do is you can actually get something like a confidence interval about models. Okay, so how do we do this for general models that have multivariate parameters is kind of a little bit stranger, but if it's a 1-parameter model, like we have so far, right? So if the models are in, let's say, is in the space of real values, right? Like we've been dealing with there. So for example, we can say something like kind of with 95% so confidence based on my assumption that the model is going to be in the range, say, of the height of students, for instance, is going to be between the average height of the students at the university is between 61 and 68 inches. Okay, and this would say something like, if I integrate over all the models between 61 and 68 inches, that integral is 95% of the entire integral space. So that means only 5% of the time would, under the data I had and the assumptions I made, would, if I'd recollected the data and resampled kind of with resampling of noise, would I have found a model that was outside this range. Okay, so to state these things, precisely, you have to kind of put all these caveats on there, and that's important to understand. But I can say this about the space of models as well. Okay, and here it's just in a 1-dimensional interval. If I had multidimensional parameters, I can have multidimensional interval, or I can quantify this in some other sort of way. But then I can say, okay, I can quantify what the true average is based on my assumptions with some confidence in some way. Okay, and so by actually writing down a probability or a PDF of what's going on here, then I get these kind of richer kind of things I can say about the modeling that's going on. And as I said, there's, how to do this and how to computationally do it. You need to often do a lot of sampling. You often can't solve for these exactly, and becomes more computationally expensive, but they could be more robust to noise. They could tell you how much noise you have, and they give you these kind of richer estimates. Okay, and so pretty much be what we'll say about this in this class. We'll talk about a different sort of confidence and concentration over the next couple lectures. But as far as these distribution of models, just to think you could apply this for the things we'll talk about the rest of the semester, but that'll be another class that will come after this one. So, okay, so great. So this is the end of the lecture. We will we'll stop here and I'll have office hours.